Okay, thanks everybody. My name is Haileleul Zeyede, and I'm going to be presenting the paper titled Why AI is Harder Than We Think, and it was written by a professor at the Sanofi Institute, Melanie Mitchell. It's going to be presented by this Haileleul Zeyede. And during this presentation, I'm going to be asking you two chocolate questions, which I call chocolate questions, in which if you get it right, you'll earn yourself a chocolate. This just to keep you awake, basically. So hint, the first one is right after the slide. Okay. So whoever gets it quickly, like Fabian, you can participate.
I'm a jury.
Just go for it. It's okay.
I think it's three, no? It's analogical.
Those are the fathers of deep learning, not really artificial intelligence.
Is it jury?
Maybe.
Maybe.
Yeah, others as well. Fabian, you want to try? McCarthy. Yeah. So it could be also Turing and also McCarthy. So you can give it to anybody else. Winston, you may have participated, but you're not here. That's why. Anyway, it is John McCarthy. And before going into the paper, for being on the same page with other students who are not from data AI, I'm going to start off by defining artificial intelligence and borrowing the term of the father of artificial intelligence, who is John McCarthy. In his paper, Artificial Intelligence defined it as the science and engineering of making intelligent machines. And people or giants who are in this field, namely Swart, Russell, and Peter Norvig, extended this definition by saying especially in intelligent computer programs. And Stephen Omohundro, who is a computer scientist and entrepreneur, also a researcher, defined AI as the ability of a machine to exhibit intelligent behavior equivalent to or indistinguishable from that of a human. So this would be a great base for us to go into the paper. So now diving into the paper, first let's look at the motivation. So when looking at this motivation, we'll try to look at the problem that the author tries to address, and we'll see if the problem is important. Okay, so first, let's try to define some terms. So AI spring. Spring is a season of transition from winter, which may be characterized by plenty, and AI spring is a period of increased interest and funding in artificial intelligence. And it's usually caused by scientific breakthroughs in artificial intelligence and maybe appealing commercial products that use artificial intelligence. Or they may be also, this season may also be caused by external factors such as environmental factors or military and strategic demands. One characteristic of AI spring is that it gives way to over-enthusiasm and unattainable predictions. By this, for example, we can see here an article from Business Insider, which says 10 million self-driving cars will be on the road by 2020. And another from The Guardian, which says self-driving cars. From 2020, you will become a permanent backseat driver. Now, these were written in 2015, 16 and 15 consecutively during the AI spring period of the 2010s. And this kind of predictions are not made only by magazines or news outlets, but also industrial giants.
So we think people do not need to touch the wheel to look out of the window sometime probably around, I don't know, second quarter of next year.
Yeah, so this promise was for 2020, but however, we are in 2023 and we have not seen a mass rollout of what has been promised. So an important thing to notice with this over-enthusiasm and lack of progress, it means that
winter is coming.
Exactly, winter is coming. And so this is followed by the AI winter. The AI winter is triggered by a combination of over-enthusiasm in the field, coupled with a lack of progress. And it causes disappointment or disillusionment and a disbelief in the prospect of AI. So this period is also characterized by a sharp decrease in funding for the research in the field and a very low number of papers published. However, this is eventually followed by a resurgence in the field. So now we can see that we are in a cycle of AI spring and AI winters. So let me give you three examples of this cycle. So there is no distinct timeline of this cycle, but it is thought to have occurred at least 3 times. So the first AI spring was in the 1960s and early 1970s, and it was triggered by Frank Rosenblatt's perceptron. So Frank Rosenblatt developed this machine, which he called the perceptron, while he was working in the Navy. And we can see this over-enthusiastic article by the New York Times that said, the Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This was said in the 1970s or 60s. You know, imagine we're in 2023 now, and this has not occurred. So this is the type of over-enthusiastic prediction that I talked about. So this coupled with Marvin Minsky and Pappert's book Perceptrons, in which they said kinds of problems solvable by Rosenblatt's perceptron are limited, in the 1970s created the AI winter. So in 1973, the reports in the United Kingdom and the United States, which were commissioned by their respective governments, found negative prospects about AI, and this led to a sharp decrease in funding. The second cycle of AI spring and AI winter started in the early 1980s, and this was attributed to the AI spring of the 1980s was attributed to the rise of expert systems. And expert systems are a type of artificial intelligence which are designed to replicate human intelligence in a specific domain. So, for example, in healthcare. And also Japan's investment in 5th generation, which is an AI initiative for research in especially natural language processing. Also US investment in strategic computing initiative, which I may discuss later on if you want, started this AI spring of 1980s. However, that was followed by the AI winter of 1990s, which was caused by the brittleness of expert systems and 5th generation and neural network not living up to its expectation in dealing with complex problems. Then the third cycle started in the 2010s due to the emergence of deep learning, which was caused by large data sets scrubbed from the web and fast parallel computing chips. And experts say that the 2020s marked a start of an AI winter because of deep learning facing situations of unpredictable errors. For example, when it faces situations that differ from the training data and its vulnerability to attacks from adversarial perturbations. Now, we are students in AI and we are in the 2020s, so you may be scared at this point because we are in the AI winter. But I say to you, my friends, do not panic, because now, since the mid-2021, new deep learning approaches, specifically transform architectures using self-supervised learning, meta-learning, and deep reinforcement learning are now being cited as a step towards general human-like artificial intelligence. Now, this falls under a fallacy that I will describe later. However, for us, it's good because it piques an interest in the general public and in governments and venture capitalists. Also, products such as ChatGPT create an interest in the general public, so the prospects of AI may be good for the coming years. So the takeaway from this motivation is that we are in a loop of AI springs and AI winters, and our prediction about the likely timeline of human-level AI reflects our biases, and these biases also show our understanding of the nature of intelligence or the lack thereof. And the author, following this, the author describes 4 fallacies in our thinking about AI, which may help us acknowledge our biases. So now let's look into these fallacies. So the first one says narrow intelligence is on a continuum with general intelligence. Now, this is what we call the first step fallacy. Okay, so the first step fallacy assumes progress towards general intelligence is kind of a linear progress and an additive progress. So Hubert Dreyfus, who is an American philosopher and a professor of philosophy at the University of California in Berkeley, noted that the first step fallacy is the claim that ever since our first work on computer intelligence, we have been inching along a continuum at the end of which is AI, so that any improvement in our programs, no matter how trivial, counts as a progress. Now, this gives the idea that every small improvement in AI capability counts as a progress towards a human-like or general AI. However, the problem with this continuum theorem is or has always been common sense. So like how to integrate common sense in machines. And his brother, Stuart Dreyfus, who is a professor in industrial engineering, I believe, made this analogy saying that it was like claiming that the first monkey that climbed a tree was making a progress towards landing on the moon. I think it's a very interesting analogy. So that was the first fallacy. The second one is easy things are easy and hard things are hard. By this, what we mean is generally we think that tasks which are easy for humans or which are easy for us may be easy for machines, and those which are hard for us may be hard for machines. So we focus a lot on developing hard machines that can perform well for hard tasks. However, Marvin Minsky, who I mentioned before, wrote that easy things are hard. And by this, what he means is carrying conversations or walking down a crowded sidewalk without bumping into strangers may be very trivial for humans, but it's actually one of the hardest tasks for machines. And on the other side, heavy mathematical calculations, which may be hard for human beings, are actually easy for machines. And this was backed by Moravec's paradox, which was devised by Hans Moravec, who is an American roboticist and computer scientist, who said it is comparatively easy to make computers exhibit adult level performance on intelligent tests or playing checkers, and difficult or impossible to give them the skills of a one-year-old when it comes to perception or mobility. So this highlights the difficulty of creating machines that can perform tasks that require common sense, for example. So the impact of this fallacy is that it is seen in all of the AI literature. And Herbert Simon, who is an American political scientist, but who had a very huge impact on computer science, was famously noted, everything of interest in cognition happens above the 100 millisecond level, which is the time it takes you to recognize your mother. By this, he is saying that to understand cognition, we do not have to worry about unconscious perceptual processing. And he is saying that the tasks that are interesting to look at are those which require above a 100 millisecond level in cognition. However, these easy things are hard, as we mentioned before, and those tasks that happen below 100 millisecond level are also interesting and exciting to look at. So I'm not going to read everything, but Hans Moravec further on says the deliberate process we call reasoning is, I believe, the thinnest veneer of human thought, effective only because it is supported by this much older and much more powerful, though usually unconscious sensory motor knowledge. So he makes the claim that those easy things that we do or easy tasks that we perform are actually hard because there is a very long duration or of evolution that allows us to do them. The author of this paper to challenge, for example, DeepMind's claim that AlphaGo triumphed in the most challenging of the human domains, mentions Gary Marcus, who argues that there are domains that, while they are easy for humans, they are much more challenging for AI systems. But I think that this is like a turning of the table argument that goes either way. So to demonstrate this, we can look at this, for example.
Robots don't feel fear. They don't feel anything. They don't get hungry. They don't sleep.
I do. I have even had dreams.
Human beings have dreams. Even dogs have dreams, but not you. You are just a machine. An imitation of life. Can a robot write a symphony? Can a robot turn a canvas into a beautiful masterpiece?
Can you?
Yeah. So this is something that I wanted to demonstrate. So this is kind of a turning of the table argument in which some would say humans can do this better than robots or AI, and others would say no, AI would perform this. So that falls under the second fallacy as well. The third fallacy is the lure of wishful mnemonics. So the term wishful mnemonics was coined in 1976 in Critique of AI by computer scientist Drew McDermott. And wishful mnemonics refer to terms or words which are used to describe human emotions or actions or associated with human intelligence that we use to describe artificial intelligence. So for example, when we look at the terms machine learning and deep learning, the term learning, we understand it as how humans learn, because it describes how humans learn in the language itself. However, machine learning and deep learning do not perform exactly as humans learn. We can talk in detail about it later, but this is what we call wishful mnemonics, assigning words which are used to, which are associated with human intelligence for machines. Another example is it was only towards the end of the game that AlphaGo thought it would win. Now, the word thought describes the process of thinking of humans in the language. However, we are using it to describe AlphaGo's performance. And other things in this area are like the naming of benchmarks after the skills that we hope that they achieve. For example, when we say Stanford question answering data set, we're not actually asking like question answering in the term like humans answer to questions. And the benchmarks test only a very limited version of these abilities. The fourth and final fallacy is intelligence is all in the brain. So this emanates from the information processing model of the mind, which is a theoretical framework that describes the mind as an information processing system. And the body does not play much into this except by providing input, which is as perception, and output, which is shown as behavior. So this is implicit in all of the works of AI through history, and it is shown in the physical symbol system hypothesis. Now, this hypothesis is developed by Herbert Simon and Alan Newell, who I mentioned earlier, and it states that physical symbol systems have all the necessary and sufficient mean for general intelligence. Physical symbol systems are much like digital computers. And there are many criticisms of this hypothesis, and notably Walking Up from the Billion Dream by Hofstadter is the most notable one. I will not go deep into it, but later on, if you're interested, we can talk more about it. Okay. Now, this fallacy leads to the speculation that to achieve human-like intelligence, we just need to bolster the hardware or computing capacity. So if we scale up the machines to match the brain's computing capacity, we may reach human-level AI. And Jeffrey Hinton, who is a heavyweight in artificial intelligence and who received the Turing Award in 2018, along with Yann LeCun and Yosha Bengio for their work in deep learning, said to understand documents at a human level, we're probably going to need human level resources, and we have trillions of connections in our brains. Now, the connections of transistors in the 12th gen i9 chipset of Intel is still in the billions of range. So what Jeffrey is saying that if we go to the trillions range, we may build machines that understand documents as humans do. Now, the author raises the case that a growing cadre of researchers are questioning this all in the brain information processing model and suggests maybe looking into embodied cognition, which proposes that the way we think and perceive is fundamentally rooted in the way that we interact with the world. So it proposes that the body is also as important as the mind. More on this is also adding emotions and irrational biases to computer systems and intelligence. And we often think of AI as this kind of pure intelligence, which is super rational. However, there is an idea of orthogonality of intelligence and goals, which says that a system may have any level of intelligence and any set of goals, but these two factors are independent. And to make, and Stuart Russell makes a very nice thought experiment in this area, which says What if a super intelligent climate control system, given the job of restoring carbon dioxide concentrations, believes the solution is to reduce human population to zero? If we insert the wrong objective into the machine and it is more intelligent than us, then we lose. Okay, so this is the second question to keep you guys awake. So what is the name of the 2014 American drama film depicting Alan Turing? Go for
The Imitation Game.
Okay, you got it. So this was the final two chocolates, so you can give it to another one, to somebody else. Okay, so now let's go to conclusion. What the author proposes for these fallacies and this problem is to go from alchemy to chemistry. So alchemy was a practice in which the practitioners used to mix different substances in the hope of achieving some or getting this global elixir, which could transform any matter into gold. So they make an analogy that we are working in, we are doing alchemy, basically working on different things and trying to merge them and create true AI. But she suggests that for a true progress in AI, we need to move away from alchemy and develop a scientific understanding of intelligence. And she says that will also answer why AI is harder than we think. And my take on this paper, generally, I summarize it here. It would be interesting to look at how these fallacies can also relate to ethical AI and how dealing with our biases based on these fallacies could help us create or develop AI that is fair, just, and respect the dignity and rights of individuals. And maybe I would suggest to look into the AI takeover fallacy, which is sometimes also called the singularity scare, which is this idea that AI will take over the world, and it's very common in pop culture. I think it overestimates the current works in AI and leads the public to believe that what we are currently working on is actually intelligence in the full sense of the word. In summary, the paper starts by describing AI spring and AI winter. It tells us that we are in a cycle or a loop of AI spring and winter. And the reason for repeating the cycles is our limited understanding of intelligence itself. And she describes 4 fallacies that helps us understand our biases in this field. So thank you very much for listening to my presentation. And we have references of interesting papers here and books. So thank you. And now I'll take your questions.